today's Carlos Nunez. Please.
All right, thanks to the organizers who are here for organizing. People are arriving, so Luis is here, so we can start. Hola. Hola. Okay, so let's go with it. Let me see if I can. Yes. All right. So the title of the talk indicates a talk on ADS-CFT. Okay. So today I will be talking about how to use holography to discuss certain field theories that start being conformal. Okay, they go into a confining regime. I don't know if you can see the point, but I will not specify with the hands, and then they lead into some screening regime. Okay, so to deal with an infinite family of n equals 2 conformal theories. By n equals 2, I will mean here 8-point Carré supersymmetry. This can be done. The thing that I will discuss today can be done for conformal theories in 2, 3, 4, 5, and 6 dimensions. Okay, but I will focus on the 4-dimensional case. Okay, then the idea will be to break this conformality, leading to a system that presents a mass gap, so no states up to some scale, and the system will be preserving less supersymmetry. Then I will focus on one example in 4 dimensions, and actually will be 2 examples in 4 dimensions, trying to get physics out of them. And like any other topic in this area, in this conference, etc., there are lots of technical aspects to this. And I will try to focus mostly on the ideas, showing not so many technicalities, but I'll ask you to interrupt me with questions, etc. And this talk is based on works with PhD students in the first line, postdocs in the second and third line, and faculty in the fourth and fifth line. So these are different papers, different combinations of people, written roughly in the last 10 months. Okay? So the talk is not very long, and the idea is that given that people have a different background, particularly different to the things I'm going to discuss, to have some time to discuss things. So please interrupt me with questions. The talk can be cut at different stages and be brought to an end abruptly. So there will be no problem if you ask questions. So let me go with this. So before many of you were in university, before many of you were in kindergarten, 1997, Maldacena conjectured the equivalence between certain certain CFT, n equals 4 super Young Mills, in particular, is the main example in that paper, and strings on particular spaces with an ADS factor. ADS 5 times S5 is the main example in that paper. And many developments follow, and very many developments follow. The ones I would like to focus attention, are these ones written here, and those are some of the initial papers that trigger the topic. In this talk, I want to focus mostly on the first and on the second items, because I will be discussing field theories with different amounts of supersymmetry in different dimensions. Our case will be 3 and 4 dimensional with different dynamical scales. Okay? And all the talk is within the setting of string theory. So let me tell you the plan of the talk, and then we'll go into it. The idea will be first to try to describe the physics problem. Okay? The physics problem is going to be how to write holographic duals, how to write non-perturbative descriptions, or if you wish, semi-classical descriptions of non-perturbative effects in field theories like Young-Mills or quantum chromodynamics. Okay? People have done things about this in the past, and I will tell you what are the unwelcome features in the models that are available. And these unwelcome features are going to be mostly singularities in supergravity or in the stringy description, so things that invalidate your description, or some behaviors that are non-field theoretical. They are stringy behaviors in the dual description. So Then I will discuss how to cure these unwelcome features. I will discuss two examples among many, many different examples recently available, where 4D CFTs are deformed into 3D quantum field theories with a mass gap, in some cases with confinement, in some other cases. I'll tell you how to calculate some observables like vacuum expected values, numbers of degrees of freedom, what you may call central charges, this transition between screening, confinement, and screening of Wilson. Okay, so this is the plan of the talk. Again, please stop me at any point with questions, as the talk can be cut short, and there are different ways of it. Okay, so let me drink some water, and let me go into it. All right. From there, can you see the pointer? Maybe I should try. I don't see, but if you see, if not, I'll point with mine. All right. So let me start setting up the problem of physics that I was describing before. So this is mostly for the benefit of the young people in the audience who were not around when these things were done. So this is 20, 25 years ago. So the problem of physics is how to construct holographic duals to field theories like Young-Mills or QCD or theories in those families, right? Cousins of those things. So the idea is that there are three possible lines that people attempt. In one of these lines, the idea is to start with n equals 4 super Young-Mills, so as I point here, and add what you may call it relevant deformation to the problem. Okay, so add an operator in the Lagrangian that makes a deformation. This operator produces an RG flow into some theory with minimal SUSY or no SUSY, and it's always Young-Mills-like. Okay, and you expect there to see phenomena like confinement, symmetry relation, domain walls, all typical non-perturbative phenomena. Okay? The holographic way in which this line proceeds is to consider a holographic background that are very large values of certain radial coordinate. I remind for some of you who might not be familiar, this radial coordinate is associated with the energy here. So at large values is ADS5 times S5 with some units of 5-4. Okay, so that's the corresponding to n equals 4 super Young-Mills. And this deformation here is corresponding to switching on in some sub-leading way, so something that goes to zero at infinity, but as you come into the interior, starts to weight and deform the geometry. The other fields in type 2B. Okay, so the 3, the axion, or the D. This produces a deformation in the metric, produces a flow that you associate with this RG flow. The main problem with this line of research is that this flow characteristically ends in a singular configuration. Okay, ends in a singularity. This singularity is telling you that you cannot rasterly calculate this phenomena using this part of the geometry. Okay, because you're out of the approximation, right? Basically, that you said. So, whilst you can learn many things about the flow, very little you can learn with that about this interesting non-perturbative. Okay. So, keep this. This is, if you think about it, very Wilsonian in the sense that you start from a CFT, you make a relevant deformation, and you flow, but it has that problem of the singularity in that holographic description. Okay. So you cannot calculate drastically. There is a second line that is quite successful. I'm going to be very sketchy here. This second line considers a two-nodes gauge theory. So by two nodes gauge theory, sometimes people refer to this as quiver, SUN times SUN plus M, with what is called bifundamental matter. So this A1, A2, and B1, B2, and some interaction between them. Okay? So it can be seen that if you put n to 0, that number n to 0, the theory is conformal, is n equals 1 conformal, and is strongly coupled. But the moment you switch on this m, it's like switching on a quasi-marginal deformation. And one can understand very precisely the evolution to the infrared of this theory. For those of you who are not familiar, never mind. This this can be explained, but we can explain it on the side, is by a set of a cascade of cyber dualities, a set of cyber dualities, and the theory ends in some SUM field theory that confines and also has a Goldstone superfield. Okay? There is, for this field theory, that is quite well understood with field theory methods, there is a holographic dual that was written by Klebanov and many collaborators, as you can read there. There is nothing I want you to remember about this, except that the background contains 4 dimensions and an internal 6-dimensional space. This goes under the name of the deformed conifold. Some other fields, some other Ramon-dimensional fields. And notice there is this work factor, H, that I'm putting there, that has the following characteristics. And this is all the things that I want you to keep in mind. When you take it to low energies, the work factor is a constant and the whole background is smooth. And you can, like in the previous case, you can reliably calculate effects, non-perturbative effects of this field theory by using this term. On the other hand, when you take it to large values of R, there is a deviation from being exactly ADS. This deviation is kind of reflected by that deformation. And this deviation appears as basically this logarithmic term in this work factor. Okay? So what this produces is that a set of calculational techniques that go under the name of holographic normalization cannot be used so easily. It's not impossible, but it's not easy. And so in this case, unlike in the previous one, things that are perfectly reliable in the infrared then become not so clean in the ultraviolet. Okay? So not so clean to carry. Right? So keep this in mind, because I'll try to summarize this in the next 2 transparencies. So one more and then we stop for questions. A third line of research that people have overtaken is the study of higher dimensional brains. In this case, would be 4 brains or 5 brains, etc., etc. And take this stack of brains, right? Say that you take 4 brains, on which a 5-dimensional Young-Mills theory with 16 supersymmetries live, and you wrap it on a compact manifold, such that at low energies, you end up with a theory in 3+1, or in 2+1, or in 1+1, etc., with different number of supersymmetries. Many people have worked on this. Let me tell you the advantage and the disadvantage. The advantages is that this is very easy to do in many different examples. So it's quite ductile thing to do, and there are many examples constructed. Another advantage is that this background is completely smooth in the infrared, so you can learn about non-perturbative aspects of this field theory by doing calculations with those backgrounds. The disadvantage, more or less you can see it in the drawing, if you consider a low energy mode here, the thing will explode, say, 3+1 dimensions with minimal superficie. As you start pumping up the energy, the modes will start entering into that compact space, and the theory will get a UV completion that will be higher dimensional field theory, sometimes string theory. Okay? So again, if you wish, here I'm trying to summarize the thing. If the ultraviolet is very well defined, like in the first of the examples I was mentioning, the infrared typically is singular. Conversely, if the infrared is smooth and trustable, the ultraviolet is not strictly asymptotically ADS, and in some cases is non-field theoretical. So that's the main disadvantages of all these things that people developed in the last 20 years. But there is another disadvantage, that is the addition of a large amount of matter quartz, namely matter transforming in the fundamental of the gauge group, is not impossible, but technically very challenging. But aside from these disadvantages, many things were calculated with these holographic duals. Some important lessons were learned, and mostly the interest of these lessons is that we have a geometric picture on certain non-perturbative phenomena in quantum field theory. Okay, so let me stop here for some questions and to drink some water. Please, whatever, please.
So when you say that the infrared is singular, what type of singularity would you encounter?
Curvature singularity, right? So it's telling you directly do not trust this superiority solution, right? So if you calculate something and your observer proves that singularity, you cannot trust that result. Please.
On the previous slide, you said that there are certain theories that kind of interpolate three different dimensions between the UV and the IR. Why? You said that was a disadvantage? Why is that?
Right. Why is this a disadvantage? Take, for example, the case P equals 4 there. Right? So this is a 4 plus 1, 5-dimensional Young. Okay. You know that theory is non-renormalized, right? You just look at the dimensions of the gauge coupling, it's non-renormalized. Okay, you say, well, okay, whatever. We are going to compactify and we are going to look at it at low energies. And you would have, say, a 3 plus 1 or a 2 plus 1, whatever, field theory, Young-Mills like with low number of supersymmetries. So at low energies, we are very safe. As we start pumping up the energy, you will encounter back this problem of the non-renormalizability. So what the system will do in the case of 4 branes is save yourself with some stringy operation. So somewhat you enter into the quantum field theory problem, some stringy problem. S-duality, T-duality, Lifton theory, etc. Okay? Yeah. So in some sense, you lose your field theory in the UV. Okay? You add something to it that saves it. All right? Any other? Dan, you have a question? No.
I do.
I
I didn't ask it,
I saw you like asking, but
I retracted it.
yeah.
Okay, so both the examples you wanted to explore strongly coupled phenomena in the deep IR.
Yeah.
But both examples you give, the UV is not, it's very far from the UV of QCD. It's not an asymptotic.
I do agree.
So I guess the challenge is, how important is the fact that you don't have the right UV to extract them?
Very good. So let me repeat the question that Daniel is asking. Is sort of a philosophical question. Both in this case, if you were interested in some SUM theory, the UV will not be an SUM theory. It's characteristically very different. Similarly here, if you are interested in some 3-dimensional field theory, the UV will not be 3-dimensional or 2 plus 1 or 3 plus 1 dimensional, let's say. So how important is this? The way I see this, and this is, again, for a philosophical question, philosophical answer, this is a feature of the thing, right? So the string theory gives you these duals, you do whatever you want, right? You work with them or not, it's a decision, okay? Good. Any other questions? If not, we continue. Okay. So let me drink some water. So the main question that drives this talk is if it could be possible to keep the virtues of these previous setups, right? The smooth IR, for example, repair the problems, repair the UV, making it asymptotically anti de Sitter, then allowing the possibility to calculate many things, and also add many flavors into the problem. The answer is in the positive. I will tell you precisely in a while where you pay the technical price to do that. But let me tell you first what's the idea here. What's the main idea? So the idea will be, it can be seen by looking at this picture, can be taught with this picture. Consider, for example, and let me put D equals 4 all along this. Consider, for example, a conformal field theory, superconformal field theory in 4 dimensions. Okay? This superconformal field theory will have some RC. What we are going to do is the following. These are 2 operations and they happen at the same time. First, I'm going to compactify this conformal field theory on a circle. Okay? So this is what I'm trying to represent here. And at the time, we are going to mix the circle with the R symmetry of the field theory. This trick is there to preserve some supersymmetry in the system. Okay? So this is what we're going to do. Holographically, this will turn into, as I will show you in a minute, some backgrounds that will contain 3 Minkowski directions, some non-compact radial direction, and a circle that will be foliated over that direction shrinking to zero size. Okay? So that will be the compactification of this circle. This circle will also be fiber mixed with the internal space. The UV is going to be ADS5, so it will correspond to a conformal field theory in 4 dimensions. The infrared is going to be smooth, so trustable, and it will correspond to a quantum field theory in 2+1, 3 dimensions. So still there is a compactification, but I can reliably calculate all along the flow, and this flow will be between a 4D field theory and a 3D field theory in the examples that I will discuss in this. Is this idea clear? Yeah? Okay. So, what I'm going to describe in the next 5 minutes is something that I could not describe, but I think is quite nice and instructive. That is, consider particular n=2 conformal theories to start with. Okay, and I'm going to describe basically what's the construction of this n=2 conformal theory. It's in these theories that I start paying the price to solve this technical problem. So you see, maybe following Daniel's question, I might be interested in a theory with 1 gauge node and 1 flavor node. I will have to consider, and I can explain why, situations like this one, where I have what are called linear quivers. So gauge groups SUN1, SUN2 up to SUNP, flavor groups SUF1, SUF2 up to SUFP, some bifundamental matter joining the nodes, making the system a full interacting system, and some fundamental matter joining with the flavor groups. The reason why I'm picking this n=2 4-dimensional conformal theories, what I'm going to describe can be done in all different dimensions, many different types of examples, is that these theories, we might share a common language, and there are many things we will know. Okay? The system is particularly nice and simple to analyze. When the system is conformal, the global symmetries of this field theory are SO2, 4, that's the conformal group in 4 dimensions. And when the system has n=2 supersymmetry, it has as what is called an R symmetry. You can think it as a flavor-like symmetry, SU2 times U1. Okay? The beta function of these theories is one loop exact, and is twice the number of colors minus the number of flavors. So if you want, for example, this first node here to be conformal, it has to happen that 2n1 is n2 that acts as a flavor group for this, plus f1. That 2n2 is n1 plus n3 plus f2. So all these equalities here have to be satisfied. Okay? And that will guarantee that this 4D n=2 theory will be conformal. There is a way of encoding all these equalities and all this numerology in one single function that turns out to be quite useful for the holographic description. So I'm going to start describing that simple function. Before that, any question or comment before I launch into it? Anything, please.
Maybe this is a stupid question.
No stupid question.
There was some relation to holomorphic plot when you do this in 3D, like when you have a circle and you twist. Is there something similar here?
I don't know what you mean by holomorphic plots in this context.
So this is like this Saratoskety, holomorphic, this could be.
Okay, very good. So the reason why I'm not picking, and then if you want, we discuss the details, this 3D system, is because these 3D theories, they become conformal only in the infrared, right? So it starts being a normal quantum field theory, and they turn conformal only when flowing to the infrared, okay? So it's not precisely what I would like to do here, but it can be done, what you're thinking, and we can discuss it as well, all right? All right, so let me discuss a way of encoding all this numerology and this type of equivalences in one simple function. So the idea is the following. So this is for a linear quiver of p nodes, okay? You can define a function that goes between 0 and p+1, okay? the function is written there, is a continuous function made out of straight lines, right? So it's what is called a convex polygonal. And the function is 0 at 0, is 0 at p plus 1, so begins and ends in 0. At 1 is n1, at 2 is n2, and like that, at p is np, okay? So you can see the function is plotted there on top. If you take the derivative of this function, you can see that it's discontinuous, right? So it has discontinuities. And if you take the second derivative, it's 0 everywhere except in the places where there are discontinuities. And the coefficient of the delta functions that appear, because one is doing the derivative of a discontinuous function, are precisely this coefficient, that coefficient, etc. They are precisely, keep them in mind for a second, the number of flavors in each one of them. Okay? So this function here then knows all this kinematic, all this numerology of this type of quiverts, right? So it knows the colors in R and the flavors in R, right? So how to use this? Let's keep this in mind. I'm going to describe how to use it to construct a holographic description of these particular conformal theories that then I'm going to deform into some infrared confinement. This holographic description has a lot of history. Started in a paper by Lin, Lunin, and Maldacena in 2005 and was completed in a very nice paper by Gayotto and Maldacena some years after. The way you can think about this is the following. You want to write the holographic dual to a 4D CFT that has n equals 2 supersymmetry, is conformal, and has n equals 2 supersymmetry, and then global symmetry SU2 times U1. So the metric, the background, must for sure encode the isometries, in isometries, the symmetries of conformality that you do with an ADS5. The SU2 times U1, you do it with the two sphere and the circle. The Ramond forms have to respect these isometries, the Ramond and the Schwarz forms, so they can live on the sphere, they can live on the circle, or they can live on the sphere and the circle. And there are, you can see, functions, F1, F2, up to F8. They can only depend on these two variables that remain here, those sigma and eta values. Okay? So it's the only way in which this system will respect the isometries that one wants to present. Correct? Now, these functions, F1 up to F8, are in principle, can in principle be determined by imposing that the system preserves 8 Poincare supersymmetries or n equals 2 supersymmetry. So you run the BPS equation, and what you find is that, okay, they are quite complicated. They are 8 first-order nonlinear coupled partial differential equations. But the following interesting miracles happens here and happens in all the dimensions. If you start operating with these functions, with these equations, putting one equation into the other, solving for one of the functions, etc., you are able, in the end, to show that all these functions from F1 to F8 can be solved in terms of one single function and its derivatives. Okay? So this single function, I'm calling it V here. Sometimes people refer to it as potential. And this is an expression for F1 in terms of B and its derivatives, for F2, etc. And there is one expression like this for all of them. All these expressions are known, and what's most interesting is that this function B solves actually linear partial differential equation. Okay? So it's a Laplace-like equation. If you remember the Laplace problem of the string on a guitar, remember that, okay, there in that case, it's not a Laplace, it's a wave equation, but you can turn into a Laplace equation by separation of variables. And remember that there are boundary conditions, the string is fixed here and there are some initial conditions, that is how you deform initially your string. Okay? So in this problem, it's very much the same. That's the equation in this particular case, it's Laplace-like. Those are the boundary conditions. And the initial condition, and this is the nice part of the problem, is that the initial condition is written in terms of the rank function of the field theory you started with. Okay? So given this system, this is a differential equation, is well posed. you can do separation of variables and solve for the potential as a Fourier Bessel series, where the Fourier coefficients are the Fourier transform of the rank function. Okay? So the way to think algorithmically about this problem is the following. Let me go back a bit. You think about the particular n equals 2 conformal theory you have in mind, right? So you fix your quiver, you fix its length, and all the numbers n1 and 2 and p up to fp. You have to make sure that these equalities are satisfied because this will guarantee conformality. With this, you write the rank function. Then you take this rank function, you bring it here, you do the Fourier transform, you put the coefficients there, that's your B function. With that B function, you put it there, you write the functions f1 up to f8, you put them there in that background, that's your holographic. Okay? And there are many checks where you do a calculation in holography and you do a calculation in field theory, and these things do match. So there are many tests that these backgrounds do encode the dynamics of this field theory. Okay? So these are the type of field theories I'm going to use as UV fixed point. I'm going to make a deformation of them that will bring them into confinement or screening or whatever interesting thing. Before I move into that, any questions or comments? Please feel free. Please.
There's also a corresponding brain construction, right? Which one can read off from the rank function?
There is a corresponding brain construction. The brain construction is more or less like this. Let me be very brief here. So there are, for a quiver with p plus 1, with p nodes, these are Nunez-Schwarz brains, Nunez-Schwarz 5 brains. Yeah. There are, in this particular case, T4 brains. Yeah, that extend there, and there are T6 brains. So, that for that quiver that I'm drawing here, that one, you have, okay, those numbers and you repeat, okay? And the immediate check that you can make is calculating with this holographic background the charges of before B6 and Nunez-Schwarz, and it will give you exactly F1, N1, and 2, F2, etc., etc. All right? Yep. So this is the first initial check. Okay, it's the first sanity check. Any other question or comment? Good. All right. I see I'm boring you, so I'll cut this short. Any other before I continue? All right. All right. So keep these field theories and their holographic backgrounds in your minds. There is no need to remember any of the details. What I'm going to do now is to take them as Wilsonian, as UV fixed point, and I'm going to deform them into a confining or screening field theory. Okay? So let me tell you first what's the idea, and then I'll show you examples where this is done precisely. So let me now then depart from this conformal world. I'm going to consider RG flows away from these fixed points, these Wilsonian UV fixed points that this field theory start. There will be along the flow less symmetries and less constrained dynamics. And the idea will be the following. Let me just sketch it with a metric of the form ADS5 times M5. So these four in all this line and in all this talk. Consider first ADS5, right? So this is ADS5 written in Poincare coordinates. The only tricky thing I have done here is that I separated 3 Minkowski directions and a circle. I separate that circle. That's the circle on which we will compactify this field theory. Okay? In the internal space, the 5 manifold, I'm separating it into some 4 manifold times a U1, and this U1 will represent holographically the U1R symmetry, some U1R symmetry within the whatever is the R symmetry of the field theory. Okay? Then we will perform a deformation on the system, and this deformation will be enacted or embodied here by this function f of r, okay, that I'm adding in front of that circle and in there. Okay? And aside from that, on top of that, one is going to pivot to mix this U1R symmetry direction with this compact direction. Okay? So this is the deformation that one is going to propose. The function f will characteristically have a form like this. I'm going to write you examples in a couple of slides. And the one form that makes the vibration will characteristically have this form. I repeat you, the idea here is starting from a 4D CFT, that's the ADS5 on top, ending up at low energies with a quantum field theory in 3D times a circle of finite size, and this circle is twisted, this is a way of saying mixed, with the R symmetry direction, and that's what this one forms. The backgrounds that we will end up with, they will have 2 + 1 dimensions, they will correspond to this direction. A radial direction, they will correspond to that direction. A circle direction that will shrink to 0 size, and the circle will be also mixed via that one form there with the internal space. Okay, so this is the general idea. And this is all very, very much inspired in works written by Anabalon, Ross, Gallerati, etc. Very nice paper by Prem Kumar and Ricardo Stuardo last year, where they enact this system in N=4 super Young Mills, and they study very clearly the field theory. And all this is inspired also by an old paper by Kazani and Komargowski, where not exactly this, but these kind of ideas are used for different purposes. I repeat, what's happening in the quantum field theory is that a UV-CFT with a conserved, and I am emphasizing conserved because it might come up later in the seminar, with a conserved R symmetry, one is picking a U1 inside that R symmetry, mixing it with the direction of which we compactify the theory, the circle direction, and thanks to this mixing, thanks to this twisting, some amount of supersymmetry is preserved. The gravity, the holographic picture that will be trustable everywhere is indicating your transition between a CFT in 4 and a quantum field theory in 3. The system will present a mass gap. And one can play this trick that I'm mentioning here in many different scenarios. It was played in many, many different scenarios. In particular, I will apply to the CFTs that I was discussing before in 4 dimensions with 8 supersymmetries. Okay? So I will tell you in what follows, there will be a couple of slides that will show metrics, right? There will be also Ramon and Nele-Schwarz fields that I will not display. They can be found in the papers. They are solutions to the equations of function, and they all enact this type of deformations in different situations. All right? Please.
So this twisting of these 2 U1s is something you can do in complete generality, theoretically, but it's not related to PSD, it's something else.
In complete generality, yes. And
Is it not related to TST? It's just something.
It's not related to TST. Okay? You could, if you wanted, do a TST on this type of things, enacting, if you want, a marginal deformation on a theory that is also confirmed. Okay? Yeah, please.
Can you see which relevant operator triggers the flow in the CFT from this geometric point of view?
Yeah. So let me repeat the question for those of you who are in the back. What you ask is, can you see precisely in the CFT, in the UV, what's triggering this flow? Okay? And indeed, because the space is asymptotically ADS, all these techniques of holographic normalization, they are very much in hand. They can be applied immediately. And you can see, and I will show you, that it's not relevant operators, but webs of operators, what are triggering the flow here. So you are putting the theory in a particular path. Okay, and that's what triggers it. Okay. Any other question or comment? How long do I have, by the way? Question?
Speaking 10 minutes.
Okay. Strictly speaking, I'll finish in 10. Okay. Any other question? Yes.
You also have an infinite set of fields now after you compactify?
Sorry.
You have an infinite set of fields, like a fields after compactification.
Which side of fields?
From scalars, or I don't know.
Yeah. So very good. So Sibyl, I think what you're asking is, okay, very good. You took this theory, you compactified. Do you know what's the field theory in the infrared? That's the question. Yeah. In cases in which the system is simple enough, like for example in this paper by Prem Kumar and Ricardo Stuardo, they start with n equals 4 superior mills. It's very nice and easy to enact this compactification and tell something about the field theory in the infrared. The most notable feature is that it develops a Chern-Simons in the infrared. So it's an n equals 2 theory with a Chern-Simons. Okay? If you wish, that Lagrangian treatment is not that useful because that field theory will be strongly coupled, right? So it's not that Lagrangian tells you everything, but at least tells you that there is a Chern-Simons term that then you can see in the holographic picture. Okay? Yeah. One more, or if not, I continue. And I'll finish in 10 as promised to go. All right. So what I'm going to show you now are just two metrics. I will quickly flash. So for orientation, and I know many of you are not into these things, so let me try to be a bit clear. Oh, sorry. Let me consider the backgrounds of the conformal theory. It contains an ADS5, a two-sphere, and a circle, and those two directions, and some Ramon and Schwarz fields. So here the deformation will do the following. Sorry. Instead of the ADS5, there's going to be a 5-dimensional metric written here. If the function f is 1, this is the ADS5, but the function f is not 1, is given there. Instead of the two-sphere and the circle, something is disturbing the two-sphere and the circle is this one form, P1, that is mixing, as you can see, lives on the direction 5. So it's mixing the U1R symmetry of the theory with the U1 in which you compactify the theory. And then there are these functions F1, F2, etc., that they are related to those in the Gayotto-Mata. Okay? So there is another system like this, is slightly more complicated. And going to your question, what's happening is that as you consider different solutions, the operators that are deforming the system are different. Okay? So there are these systems that they are written, they solve the questions of motion, so everything is trustable here. And following your question, you can calculate, okay, now that I have this trustable system, can I learn how I deform the thing? And indeed, you can learn this is just by holographic normalization, that in the first slide, in the first transparency, the first metric I show, there is a dimension 3 operator that is getting a bed. In the second slide I show there is a dimension 3 and a dimension 2 operator. You can also decide to break supersymmetry by giving expected values to T mu nu, and that depends on one of the parameters. Let me try to close this. I'm not going to tell you about many of the things that I have in the end of this talk, but let me try to tell you about one thing that is at least interesting from a field theory viewpoint. One may wonder, so here, one is having a field theory that starts being 4-dimensional and ends up being 3-dimensional. This field theory, in these particular cases, first confined, then there is a screening phenomena that is part of what I'm not going to discuss now. And you may wonder if one can write a quantity like a central function I remind you in conformal theories, measures the number of degrees of freedom of such conformal theory. So you may wonder if you can write a function that measures the number of degrees of freedom, not in the conformal theory, but all along the flow. Okay? The problem is that because this system breaks Lorentz from SO13 into Lorentz in 2+1, this is quite a hard problem to tackle in a quantum field theory formalism, because you are breaking Lorentz. Sorry, you had a question. Sorry. You are breaking the supersymmetry. So notice this. Notice this. in this function, I have a parameter, mu, okay, that I can choose to make 0 or not. If I choose it to make 0, supersymmetry is respected. If I choose it not to be 0, then supersymmetry will be broken, as you are correctly observing there.
So this is actually relating to crypto.
So the twisting is there, this mixing is there, irrespective of the fact that I could or could not break supersymmetry. What you are saying that is very correct is that if I do not do the twisting, supersymmetry is for sure broken. Yeah, okay? Yeah, very good. Very good. Very good. Any other? Okay, so let me try to finish with this. So there is this problem of writing central charges, central functions for conformal theories has a long story and actually started pre-ADS-CFT with a paper of Brown and Enoch that 10 years before ADS-CFT, they wrote a formula, let me write it here, where the central charge of a CFT into D, they were associated with the inverse Newton constant of some 3D graph. Okay? Yeah. Formulas like this then were much advanced, right? So this is 1986. Comes ADS-CFT, this gets a complete resignification. And people realize with time that it's possible to write something like a central function for theories that are not necessarily conformal, something that gives you an idea of the number of degrees of freedom. Okay? So you use those formulas in these backgrounds here, right? Either this one or that one. Okay? And the result that you get is quite nice for different reasons. Let me just flash the result without showing you any detail of the calculation. The result is a product between the central function of the UV CFT, whichever is the CFT you chose, this will appear there, times a function that depends on the flow. In particular, in this case, is this function f here or that function f there. Okay? So you just take that seriously, you plot or just draw this function, and you find something that for large values of R, say in the UV of the system, takes the value of the CFT in 4D, the central charge of the CFT in 4D. As you take it to the interior, this starts to decrease and is monotonic and ends up at 0 because at some point this function f vanishes. Okay? So that's in the far IR, there are no degrees of freedom. This calculation is quite non-trivial. There are many cancellations that happen, but everything in the end manages to accommodate in that way. And just let me mention, just to go closing this, that this factorized form that this particular observable is displaying, actually, this factorized form, the form as a product of two parts, one referring to the UV and one referring to the flow, occurs also for many other quantities. For example, occurs in some Wilson loops, in some entanglement entropies, in complexity, in many different things you can tell. These universal behaviors are quite non-trivial from the viewpoint of field theory, right? It would be quite difficult to predict this from field theory. And one might think that they're actually consequence, and it's very nice to make the relation, with a conjecture that Gauntlet and Varela did in 2007, completely in the context of supergravity, and then very much in the context of supergravity was proven by Casani, Petrini, Waldron, etc. So I insist, this is very non-trivial from the quantum field theory point of view. So let me tell you the things that I am not going to discuss for you. And then I'll close it, and I think I'm in time. Kostya? Yeah. Yeah, so let me tell you things that I'm not discussing. If you want, you just catch me anytime after the talk, or you ask me after the talk, or you ask me now. So I'm not going to discuss some interesting, very interesting effect that happens to Wilson loops. I'm not going to discuss some very interesting thing, very interesting triangle of consistencies that happens to super QCD-like theories. This is now I wrote out there an outlier because this system has nothing to do with the ones we are discussing. And I'm not telling you about screening, right? So I only show you very nice pictures and all very nice, but I'm not telling you how these systems do see screening of the Wilson. So just to close, I have presented in 4D a formalism that is useful to write conformal holographic duals to conformal theories in all the possible dimensions, 1, 2, 3, 4, 5, and 6. I have shown how to use these CFTs as a UV fixed point and then perform an RG flow that falls into a gap theory. There are many observables that can be calculated in the CFT that they are quite interesting along the flow. These are some of the things I didn't tell you. Some of these observables are universal, some are not. And it's interesting to better understand the dynamics of these things in the presence of the flavor degrees of freedom. I'm presently exploring these things with and without supersymmetry in different situations. Thanks very much. Sorry for holding you so long.
Yeah, some function in the metric that turns to 0 at the end of the flow, it typically means that there is a horizon. Is it?
It is the case here. Indeed, what happens here is that, let me take this down. So what's happening here is that, as I mentioned, right, there is this radial direction, there is this circle on which we compactify the theory. And at some point, that circle ends. Okay. So one needs to be careful to pick the periodicity of the circle, such that when you expand things here, it looks like this. So like flat space, meaning that ends in a smooth way. Okay. Typically, all these confining or this type of backgrounds, they all play this trick in circles or different things. Okay. So you may call it a horizon, right? I don't call it a horizon, but I don't like, but you may call it, and you can make the analogy of what happens here to what happens in horizon of a black hole with the time circle that also shrinks to 0 size in a smooth way. Okay? Yeah. Any other?
So I think for 40 n equals to 2 theories, there are also two-dimensional twists. Sometimes they are topological holomorphic twists, for example. So is it has it been done, like the sort of flow to the IR of such twisted theory?
Very good. So your question is, I have a 4D theory, say a CFT, yep.
Yeah.
And I compactify on some to mine.
Yes.
In such a way that if this had some amount of SUSY, this will have some fraction of that amount of SUSY.
Yes.
Yeah. Yeah. So holographically, you can do this. You can do this when this is a hyperbolic to space or a to sphere, etc. This was done. It doesn't proceed exactly as what I described. It's a bit more complicated. Yeah, but it has been done. It has been done. Let me say something here. This has been done a lot in the case in which here you end, say, with a CFT in 2 dimensions. For situations where the theory in the infrared is confining, it's a bit more difficult to do. Okay? Yeah.
Right.
But in the case of CFTs in the infrared, it has been done many different ways. Okay? Yeah. Daniel.
So you have this nice expression for an effective central charge.
Yeah.
But I guess I'm slightly confused about one thing, which is you're comparing a 4D C, which is a well-defined thing in 4D,
Yeah.
which doesn't exist in 3D. So what is the thing that you're actually making?
Yeah, very good. Very good. So the question that Daniel is asking is the following. I drew a plot here. I don't know if this can be seen. I'm going to change the color. I drew a plot where this was the end of the space. That was the value of the 4D CFT central charge. And I drew something like this, right? Okay. So notice what's happening here is quite subtle. If you take a 3D field theory, yeah, And this 3D field theory happens to be somewhat completed by a 4D field theory, conformal. This 3D field theory will see infinite number of degrees of freedom, right? So if you were a 3D person, you do not realize that suddenly what is happening is that Kaluza-Klein modes are appearing and there are infinite of them, but actually they are an extra dimension, okay? This quantity knows it. And this was constructed with that in mind, right? So in particular, that's why this goes a bit away of Brown and all, right? But this is what this quantity is doing, is telling a system that starts in a given dimension and is completed by a higher dimensional system, know that these infinite Kaluza-Klein modes, they're actually an extra dimension. And that's why, as you pointed out very correctly, the system starts being 2 + 1 dimensional and suddenly knows something about the 4D, right?
Yeah, I guess my more point is, what would you calculate directional field?
Yeah.
The partition function on the sphere or?
Yeah. So this would be the partition, but notice that the sphere here is not the four sphere, is not the free sphere, right? So it's tricky in that sense. Yeah. Probably in a 3 times S1, this will work. Yeah. Okay. Yeah. One more. No, sorry. Shout me that I don't hear.
Can you say any interval structure
About the?
about this twisting construction or the breaking of symmetry?
Yes. So in these systems that I show you, in these particular ones, you start with a 4D CFT with 8-point association, and you end with a 3D quantum field theory with 4-point association. So this is what you may call an n=2 system. In these particular cases, actually, you can play this in different dimensions with different numbers.
I mean, is there any integral structure?
Integral structure.
Yes.
Yes. You can. So by integral structure, you mean G structure, what I call G structure, SU2 or SU3 structure, G structure, or what you mean by integral structure?
Can you construct like an infinite conserved charge?
Okay. Very good. So you're asking different from the one I was thinking. So what you're asking is there integrability in any of these systems? I just realized this is an integrability conference. So no, but very good. It's very good. So look, you can play the following thing. Let me draw it here. You can play the following thing. Start with a 4D system that is actually integral. Okay. And belongs to this class of metrics I was drawing. Okay. So there is one example of this that is actually that was written. By these two gentlemen. One of them is behind you, the other is in front of you. Okay? So you can play this game that I was doing here and deforming this, performing exactly this deformation to the Festos-Thomson system, and it will give you something. Okay? It will not preserve integrality. It will not preserve integrality. This particular deformation. Okay? Yeah. All right.
It's not can be in certain twisted preserve integrity.
No, the twisting, you can do this thing with the deformation, with the twisting, etc., and it will not preserve integrity. So you can check, this is probably something you're familiar with. You can check strings that move in this pattern and look for on the worksheet of this string if that system is integral, and you will find that the more the string explores the infrared, the least integral it becomes. So it's non-integral. It turns chaotic as it explores the infrared. Am I answering your question? Okay, we can talk it.
Yeah, we can check later.
Thank you very much.
Carlos again.